The third and final system for identifying hazardous materials is the National Fire Protection Association's 704 ID system, and that's what you see here. So it doesn't look like a placard from the Department of Transportation, and it doesn't look like a label from the Department of Labor, and that's where this one is different. So I'm going to introduce to you the National Fire Protection Association ID system. It's really straightforward. And then demonstrate how to use the emergency response guide. And this is where we're going to start to put some of these different pieces together. So the 704 system was designed to minimize loss, whether that be human loss or property loss, at a quick glance. And so it's made for these first responders, where the global harmonization system is tailored to workers, and Department of Transportation is emergency responders, but shippers and receivers as well. And so the system is not mandatory, it's voluntary. It's more of a consensus standard. However, everybody pretty much follows it because, as you will see at a glance, you can see what the numbers and the symbols mean once you understand them. And my bet is many of you, when you looked at the diamond, you pretty much figured out that red was for fire. Now, the one you might have gotten incorrect was reactivity being yellow, health is blue, and then the special notation is white. And so in this instance, it's opposite of the global harmonization system, and the higher the number is more dangerous. And so for whatever we're looking at here, gasoline, we know that its main hazard is fire. And so now we're pulling it together. We have Department of Transportation placard for gasoline. The United Nations number is 1203. The reason why I circled this is because flammable liquids tend to be lower numbers. Gases tend to be 1000s, and then you get into your flammable liquids at 1200, and it kind of goes from there. Not that you have to know that, but it's just something that you'll start to see. And so if we could look at all this together, so on the back of the truck we know it's a flammable liquid. Look it up in our handy dandy book. We find out it's 1203, it's gasoline. And if it was not on a transportation truck but on a large storage tank, then the symbol would look the same here. Somewhat of a health hazard, very minor, not reactive, no special considerations, but a high fire danger. And so then if we get really close, yeah, we could see it. So again, remember, these are all standardized. We have the flame, we have a caution sign here, and then we know that it's a health hazard. So highly flammable liquid and vapor causes skin irritations, may be fatal if swallowed, may cause cancer, suspected of damaging fertility or the unborn child, may cause damage to your reproductive organs. You probably didn't know that about little old gasoline. And then we have so our signal word. No, that's not right. That's not your signal word. My apology. Your signal word is the exclamation point. But then again, on the label, it does give you some really quick, basic first aid, as you would expect to find on a label. Ooh. There we go. So there's more detail, but basically, you can see that everything is 0 to 4. So for health hazards, remember, this is for the emergency responders. So think about the firefighter who's going in, right? That's why it's a different kind of placard system than the Department of Transportation. So too dangerous to enter vapor or liquid would be a number 4. Our gasoline was a number 3 for flammability, ignites at normal temperatures. And that's not the highest hazard. The highest hazard is extremely flammable. But it's really this yellow category we have to look at, because reactivity just makes everything else a little bit more spicy. It could cause your flammable liquid to detonate, or detonate because of a strong shock. And it could be unstable if heated, or zero would of course be normally stable. So again, the higher the number, the higher the danger, which is opposite of the global harmonization system. So we're pulling these together. Now we have our warning label that's similar to global harmonization system, but not completely. But the NFPA placard, or the NFPA diamond, is on there, and then the placard for ethyl alcohol is 1170. You already know, you should just see this already, you know a 3 is a flammable liquid. And then you can see that it's a flammable liquid, minor health hazards, pretty much the same as gasoline. And this is kind of neat where they have the codes over here, made simple, just a quick glance so you don't confuse the different numbers and the different orientations. All right, so what do we have here? Something really nasty. Chlorine and fluorine, they like to react and bond to other molecules. And when you hear chlorine or fluorine, think dangerous, toxic gas. And so 1749 is chlorine trifluoride. And it's number 2, so we know it's a gas, and it's got the skull and crossbones, so it's toxic gas. And then the other placard that would be important here is you'd have to have the inhalation hazard on there as well. Even though it's a toxic gas, doesn't necessarily mean that it's an inhalation hazard. And even if that was true, you would want to have that extra warning, just like dangerous when wet. So this is also an oxidizer, so that it reacts with other agents. It makes burning more powerful. That's how you get explosives. And it's a corrosive. So a toxic gas that makes flammable material more flammable, and it's a corrosive. That's a lovely one. Okay, so my first stop is Cameo, chlorine trifluoride, and there's the placards that go along with it. Inhalation hazard, oxidizer, and a corrosive. And you can see that it tells you what DOT hazard labels that you need. On the back of the vehicle, not usually, on the back of the vehicle, you only need the first one, and that's why inhalation hazard's there. Oxidizer and corrosive wouldn't be on the back of the vehicle, even though they are other important health hazards. And then you can see when we're looking down that the NFPA placard would be not quite viewable. There we go. Well, okay, so 4, it can be lethal. Flammability, will not burn under typical fire conditions. However, that's where sometimes these are really interesting. Capable of detonation or explosion, decomposition, or explosive reaction, but requires a strong initiating source, or must be heated under confinement before initiation. So that's where you have the instability, or the 3 right in here for reactivity. And with W means reacts violently or explosively with water, possesses oxidizing properties.
Our YouTube channel, and in the video today we're looking at setting fire to glass, the NOPE chemical that is chlorine trifluoride. First discovered back in the 1930s, chlorine trifluoride is a rather curious chemical that easily reacts, sometimes explosively, with just about every known substance on Earth. Just to get the ball rolling, here's a few of the more unusual things chlorine trifluoride is known to set fire to on contact: glass, sand, asbestos, rust, concrete, people, Pyrex, cloth, and the dreams of children. Obviously, the first question to answer here is how chlorine trifluoride is somehow able to cause asbestos, a substance that is known for being almost completely fire retardant, to catch fire. Well, that's because chlorine trifluoride is a more powerful oxidizing agent by mass than oxygen itself, meaning it's capable of rapidly oxidizing things that would normally be considered practically impossible to set aflame, like asbestos. Chlorine trifluoride is such an effective oxidizer that it can even potentially set fire to things that have seemingly already been burned up, like ash or spent charcoal. The substance is so highly reactive that famously unreactive elements like platinum, osmium, and iridium will begin to corrode when they come into contact with it. Notably, tough elements like titanium and tungsten are also regarded as being wholly unsuitable to storing the chemical because they set on fire as soon as they come into contact with it. The only known way to store chlorine trifluoride safely, which we use in the loosest possible sense, is to put it inside of a sealed container made of steel, iron, nickel, or copper, which are able to contain the chemicals safely if they're first treated with fluorine gas. This is because doing so will coat the metal in a thin fluoride layer, which the chemical won't react to. However, if this layer is compromised in any way, or the metal isn't completely dry, chlorine trifluoride will begin to react violently and cause the vessel to explode. A few of the other things known not to react with chlorine trifluoride include liquid nitrogen, the inert gases, and polychlorotrifluoroethylene. Rather fortunately, chlorine trifluoride doesn't react with air unless it happens to contain a larger than average amount of water vapor. Speaking of which, when chlorine trifluoride comes into contact with water, it will react explosively with it, and as a fun byproduct, creates large amounts of dangerous gases such as hydrofluoric acid and hydrochloric acid. Hydrofluoric acid in particular is incredibly dangerous, and along with being able to melt things like glass and concrete, can permanently damage your lungs and eyes. As if that wasn't worrying enough, if you're ever unlucky enough to get hydrofluoric acid on your skin, it doesn't actually hurt until a few hours later. After it has absorbed a bit, it starts destroying your nerves and bones and can ultimately cause cardiac arrest when it gets into your bloodstream. In fact, in 1994, a lab technician in Australia accidentally spilled hydrofluoric acid on his lap, and despite immediately executing safety procedures, including hosing off, immersing himself in a swimming pool, and later extensive medical care, including needing to have one of his legs amputated, within 2 weeks of the accident, he was dead. Unsurprisingly, the Nazis were really interested in the military applications of chlorine trifluoride. After all, it's a substance that reacts explosively with water. Humans are largely bags of water, and for those that don't come into contact with it directly, there's the byproduct of the deadly gases. Further, there is really little one can do to put out the fires it causes directly, other than to let them burn off. If you throw water on the source of the problem, it will get worse. The reaction here also doesn't require atmospheric oxygen to burn, so trying to use that method of fire suppression won't work either. Though chlorine trifluoride was thankfully never used during combat, the Nazis did succeed in creating several tons of the stuff in a secret facility known as the Falkenhagen bunker, before it was captured by the Russians in 1944. The Nazis working in the Falkenhagen bunker referred to chlorine trifluoride simply as Substance N, or N-Stoff, and were planning to store it inside specially designed shells which could be used in battle. According to reports released by the Soviets following World War II, Nazi trials involving Substance N were promising, but of course the weapon was incredibly dangerous for those carrying it around too, not just those they launch it at. As an example of the kind of devastation chlorine trifluoride can have, you need only to consider what happened when almost a ton of this stuff was accidentally spilled inside of a warehouse in the 1950s. According to eyewitness reports, the chemical burned straight through a foot of concrete and 3 feet of gravel, while simultaneously releasing a deadly cloud of gas containing a cocktail of chlorine trifluoride, hydrogen fluoride, chlorine, and hydrogen chloride that corroded every surface it came into contact with. After watching this video, you're probably wondering what possible purpose this chemical could serve that doesn't involve trying to recreate a scene from a Michael Bay movie. Well, due to the fact that chlorine trifluoride is such a great oxidizer, there have been several attempts to use it as a low-cost, lightweight rocket fuel, starting with the Nazis, who used it to propel torpedoes. Of course, it's so difficult to store safely that it's generally considered not to be worth the risk for this usage. After all, while you'd need to use less fuel thanks to its extreme oxidizing capabilities, if you had a rocket accident, you'd potentially be spewing tons of this stuff all over the place with no real effective way to deal with the situation. For instance, after studying and experimenting with this chemical for rocket use, rocket scientist Dr. John D. Clark famously said about the best way to deal with potential chlorine trifluoride rocket accidents. He said, "I've always recommended a good pair of running shoes." There are a couple of other useful applications though. For instance, it's great for plasmaless cleaning of certain surfaces used in semiconductor manufacturing, and it also works well at cleaning uranium residue off the walls of nuclear power plants and removing built-up oxides. So I really hope you found that video interesting. If you did, please do give us a thumbs up below this video, and don't forget to subscribe to our channel if you haven't already. Also, over there on the right are a couple of other videos you might enjoy if you enjoyed this one. Thank you for watching.
Germany, 1939. In a secret bunker on the German-Polish border, Nazi agents were overseeing the production of a recently discovered chemical they'd codenamed Substance N. It boiled when they exposed it to air, it exploded when it touched water, it was lethal when inhaled, and when it decomposed it spit out deadly hydrofluoric acid. When loaded into a flamethrower and ignited, it could burn at temperatures over 2,400 degrees Celsius. The plan was to arm troops with Substance N and use it to melt Allied bunkers into hot porridge. But then after studying it for a while, even the German soldiers were like, whoa. Experiments with Substance N were discontinued because the Nazis decided it was too dangerous to work with. Should give you some kind of sense of what we're dealing with here when we talk about the most dangerous chemicals in the world. I'm talking about things that explode when you touch them. Things so poisonous that if even a millionth of a gram went up your nose, it would end up killing you. Things that could even disable you because of their totally debilitatingly horrifying smell. And yes, chemicals so severe that even the Nazis thought they were crazy. Let's start with what the Germans had in that secret weapons bunker. They originally planned to produce 90 tons of the stuff every month, but only made about 30 tons throughout the whole war. What they concocted was chlorine trifluoride, the most vigorous fluorinating agent known to humanity. Fluorinating agents rip other molecules apart to replace their hydrogen atoms with fluorine. The result is what chemists call a violently exothermic reaction, in this case known as a fluorine fire. It's much more dangerous to handle than even fluorine gas, which, as anyone with a degree in chemistry can tell you, is not a sentence that you get to say very often. It's also a better oxidizer than oxygen. Oxidizers are compounds that steal electrons from other chemicals in a reaction, and they are what make combustion possible. Chlorine trifluoride is so good at this that it can burn stuff that sane people might think of as non-flammable, like bricks or asbestos, or things that have already been burned. Oxidizers are also used to ignite rocket fuel, and in the very short time that US rocket scientists thought about using this stuff as a propellant, they quickly learned that this idea was bad. In the early 1950s, the first time that US scientists tried to ship chlorine trifluoride in bulk, the steel tank cracked and a full ton of it spilled out. It burned so hot that the chemical ate through an entire concrete floor, and then a meter of dirt and gravel beneath that. One eyewitness described the spill only by saying, "The concrete was on fire." Chlorine trifluoride is still manufactured and is used by semiconductor companies to clean their equipment to within an inch of its life. The good news is that you can store it safely in a regular steel drum, as long as it's airtight and you're you're really, really careful, because it instantly scorches the inside lining of the container, leaving behind a non-reactive plating of metallic fluoride. Non-reactive is not a word that we're going to need when discussing the next chemical on our list, azidoazide azide, the most explosive chemical compound ever created. This twitchy little compound is part of a class of chemicals known as high nitrogen energetic materials, and it does what it does because nitrogen just wants to be left alone. A nitrogen atom bonded with another nitrogen atom is one of the most stable molecules on Earth. Their electrons form an extremely strong triple bond with each other, which in nature can usually only be broken by a molecule being hit by lightning. The strength of that bond means that when two nitrogen atoms snap together, they release a tremendous amount of energy. So if you look at a molecule of AA, we're going to call it AA because azidoazide azide is hard, you can see how it gets its bang. It has 14 nitrogen atoms, and because of the way the molecule is structured, none of them are in a triple bond. Instead, they're stuck in a loosely bound high energy state and are dying to move to a more stable lower energy state, which means releasing a lot of pent-up energy in the process. As a result, AA is both highly reactive and hecka explosive. How sensitive is this stuff? Well, it's actually hard to say because it's too sensitive even to measure how sensitive it is. A team of German chemists created it in 2010 with the help of the US Army in an effort to develop more energetic compounds. And their first report on the discovery, they said, and I quote, "The sensitivity of C2N14 is beyond our capabilities of measurement. Even the smallest possible loadings in shock and friction tests led to explosive decomposition." To give you a list of how touchy this stuff is, here's a list of things that make azidoazide explode. Moving it, touching it, dispersing it in solution, leaving it undisturbed on a glass plate, exposing it to bright light, exposing it to X-rays, putting it in a spectrometer, turning on the spectrometer, and my favorite, absolutely nothing. They had it in a shock-proof explosive case in a dark climate control room, and it blew up. I think somebody said something mean about it somewhere, and it was like,
Okay, the full explanation of the health effects is here, and there's your example of hydrogen cyanide that is in a compressed gas cylinder, material that on very short exposure could cause death or major residual injury. And it's also a fire of 4 as well.
The world's population is growing, and for many, living standards will continue to improve. As a result, global energy demand is expected to double by 2050 when compared to 2000. To help meet this demand, gas will form an increasingly important role. Natural gas is plentiful, and it's the cleanest burning fossil fuel. But some natural gas resources are in remote locations. Transporting the gas long distances by pipeline can be costly and impractical. The solution? We liquefy the gas by cooling it, which shrinks its volume for easier, economical, and safe transportation by ship. So how is liquefied natural gas produced? Natural gas extracted from the ground contains impurities, water, and other associated liquids. First, it is processed to clean it. It goes through a series of pipes and vessels where gravity helps separate the gas from some of the heavier liquids. Other impurities are then stripped out. The natural gas passes through a water-based solvent that absorbs carbon dioxide and hydrogen sulfide. These would otherwise freeze when the gas is cooled and so cause blockages. Next, any remaining water is removed, as this would also freeze. Finally, remaining lighter natural gas liquids, mainly propane and butane, are extracted to be sold separately or used as a refrigerant later in the cooling process. Traces of mercury are also filtered out. Now the purified natural gas, methane with some ethane, is ready to be liquefied. This happens in heat exchangers. A coolant, chilled by giant refrigerators, absorbs the heat from the natural gas. It cools the gas to minus 162 degrees centigrade, shrinking its volume by 600 times. This turns it into a clear, colorless, non-toxic liquid, liquefied natural gas, or LNG, that is much easier to store and transport.
So let's take a look at the flammability category at the top of our diamond. 0, material will not burn. 4, material that will rapidly or completely vaporize at atmospheric pressure and normal ambient temperature, or that are readily dispersed in air and will burn readily. So propane comes right out of the bottle as a gas, and it's ready to burn. All it needs is an ignition source and chemical reaction, and of course something to propagate it. So the yellow zone is the one that can really amplify all the other physical characteristics once something is reactive. And so we have number 4, material that in itself is readily capable of detonating or of explosive decomposition or reaction at normal temperatures and pressures. And an example would be TNT, and that's why it is shipped wetted, so that it isn't reactive. And so right from the hazardous materials book, you can see the GHS system, the signal word as well as the hazard statements. You would now be able to look these up and find out the hazard statement for each one of them. And then we're kind of down to our last one, which is the special category. But before we move on, can you identify each one of these? Oxidizer, corrosive, toxic, health hazard. Again, you know where to find those. And then you should be able to identify these as well. It's a gas, inhalation hazard, toxic, an oxidizer, and a corrosive as well. And you could see that in here where there's no flammability rating, but the other points on the diamond are filled in. So the last category is the other category, and it's right there at the bottom, and oxy means it's an oxidizer, so that's noted as well as saying something in the reactivity category, 1 or 0 through 4. Excuse me. A W means that it will react with water, and the propeller symbol is radioactive. It isn't the biohazard. That one's a little bit different. And then you see the double symbol right down here where it will react with water, and it's an oxidizer. So reacts violently with water, magnesium metal. Ammonium nitrate is a very strong oxidizing agent. And so I would say that this slide is the most important one of the series, and you should probably have it available to you when you take a quiz or something, because it certainly simplifies what we're looking at. And so we're going to look at one more identification system, and I love this picture because it must be 23 years old, and it's so fun seeing my old dogs. It reminds me of how long I've been teaching hazardous materials. So what does this tell us? And what does it go on? So your answer should be it's a placard on a transportation vehicle, it's a flammable gas of some kind, and when I looked up the United Nations number, I found out that it was liquid propane, so 1075. And how about this? Well, this was liquid propane as well, which is non-reactive, no special considerations, can be an irritant, but will burn readily, right? So this goes on the storage tank, this goes on the vehicle. Okay, now what does this one tell us? Oh, I wish I could hear your answers. Well, it's not flammable. It's a mild health hazard, but it's an oxidizer and quite reactive, right? 3 out of 4. And so this is the symbol for ammonium nitrate, which is a very strong oxidizer. Contact with combustible material will increase fire hazard, although in and there of itself it is not flammable. That's the cool thing about the oxidizer. It just makes stuff more reactive. So now we're going to move on. We finished the NFPA, and we're going to move on to the emergency response guide.